Hey everyone, welcome back. So we're going to turn to our last topic in this second semester calculus course. And this topic is very powerful. You know, everything we're about to do is leading up to this big result. You maybe even heard of these called the Taylor series or Taylor polynomials. The idea is this: what do we know about polynomials? From a mathematical perspective, the theory of polynomials is pretty complete. We have exhausted so much. And think about a derivative or an integral. If you can choose any function other than a constant function to differentiate or integrate, gosh, polynomials, they are simple. What's fascinating is that if you give me a function that has the right conditions, well-behaved, smooth, differentiable, all those things, then give me some point in its domain, and I can write that function, no matter how complicated, as a polynomial. And that's remarkable. To be able to write a function, at least on some small interval, as a polynomial. That totally changes the practicality of a lot of the computational challenges that we face. Think about, Simpson's rule. Think about these functions that maybe we could write as a polynomial and have some better ability to employ the fundamental theorems of algebra. There's just all sorts of options available to us. And so to do that, we really want to treat what will be known as the Taylor polynomial as a series, meaning a sum of terms, an infinite sum, really. And then to talk about a series or a sum, we need to start by talking about sequences. And you've seen that a little bit with limits, but we're going to really deepen our understanding. And to do that, there's really a couple of threads. There's a theoretical side, which sometimes will be very intuitive, other times not. And you're not going to see me prove as many theorems now, just simply because they're a little more technical in nature. But you will prove them later in your first analysis courses if you are a math major or need to take that type of course. So you will see them, but for now I'm going to appeal highly to your intuition. And then there's verbiage. There's just a bunch of vocabulary that is meaningful and we need to have command of. And so you'll see kind of that dual thread as we move forward and then as we employ some of these big results. So let's start with sequences. Okay, so we want to talk about infinite sequences and series, and we want to start by talking about sequences. So what is a sequence? Well, really, a sequence is an ordered list of numbers. And then there are different notations for sequences, but really, if you think about, let's think about a sequence, whoops, I don't want red. Let's think about a sequence as maybe a function. Well, the domain is typically, and depends. I'm going to write this. Some people might take issue, but sometimes you might not start at 0. Sometimes you might call the first term A1. It just depends. But essentially, think non-negative integers or natural numbers or counting numbers. It's essentially the domain. And usually, you denote them by some rule, maybe, AN. Call it A subscript N. And what that really means is if you have a list, A1, A2, see, I'm starting at 1, not 0. It just depends, but it's a matter of taste sometimes. AN, and so on. So it's ordered. okay? You might see notation like this with parentheses. You might see notation like such, or you might even see like a list. Different notations. The big idea is, does this thing converge, right? The sequence may have infinitely many terms, but after long enough, do all the terms start to approach some value? Do they all start to look alike? And that's what we mean by convergence. And if that doesn't happen, then we say the sequence diverges. So let's unpack this definition a little bit. So let's say that I've got some sequence, and I don't know, maybe it does this for a while. And so it looks like, it appears that my limit is essentially this value. And it might keep going down and up. That's too far away. And when we say convergence, notice that essentially at some point, all of my sequence values are pretty darn close to L. Now, pretty darn close to, that's not really a mathematically rigorous term. You're not going to find that in a dictionary of mathematics. Pretty darn close to. However, your intuition certainly can be appealed to, and we can formalize pretty darn close to. So look what happens. I could do this. Let's say that I had a bouncing ball going up and down around L. And at some point, I tell someone to yell, stop. And so I'm going along, and all of a sudden someone says, stop. Okay, so they've stopped. I've got this, and I've got this. And so what happens is I've created a band around L. And notice that after a certain point, in this case, it looks like after this one, all of the values of my sequence lie inside this band. And so for all my n's bigger than this n, my ANs are in this interval L plus, oh, I'm sorry, L minus a little bit and L plus a little bit. Yes, that's a question mark. Well, I could do this again. We could say, in fact, we could take and make a smaller distance here. I could say, let's go, let's not do that. We could say, let's take and, I don't know, make this our n. I'm sorry, make that our width around L. So I built an interval around L. And sure enough, eventually, all the points sit inside that interval. And so what we can do is we can say, all right, it doesn't matter how small that interval is. Eventually, all the terms of my sequence will be inside that interval. And what we do typically is and those of you math majors are going to love this, but we call that interval, we say it has length epsilon. It's the Greek letter epsilon. And so what we really are doing is we're saying, okay, there comes a point where all my sequence values are between L minus epsilon over 2 and L plus epsilon over 2. And then if you let epsilon go to 0, you just start squishing. And again, I can draw any number of red lines on here, and eventually the terms of the sequence will sit inside that epsilon band. Okay, that's the idea of convergence. Now, if that doesn't happen, if we can't capture all the values at some point and thereafter, then we say it diverges. And so this really leads us to this formal definition. And you're gonna, those of you who are math majors going on into graduate school, this definition is so powerful and so deep, and it doesn't go anywhere. You know, I would say in my own experience, it took me years, probably, if I'm honest, graduate school before I fully appreciated just how deep this was and what it's actually saying. But this is what we mean by convergence. For all epsilon greater than 0, I can find some integer n, so far enough out on this axis, so that after that point, all my sequence values live inside this band, okay? Now, who knows what they're doing before? I mean, they could be doing all sorts of stuff, but after this value n, they're all trapped, okay? And because this says for all epsilon greater than 0, then those epsilons can be arbitrarily small, infinitesimally small. And that's why we say what the limit value actually is, okay? All right, here's one. So you've got f of x equals L, limit as x goes to infinity. Something we're comfortable with, we've seen in really probably a Calc 1 course. And now we're saying, okay, if f of n is equal to an, in other words, when I plug integer non-negative integer values into this for x, I get the same limit, which should make sense, right? Let's think about, and this is just a sketch of a proof, but let's say I've got some limit. I'm gonna call it this. This is my limit L, okay? And let's say I have some function that eventually starts to approach that value L. Well, remember what's happening here. My function f of x, right, is defined for all real numbers. And what we're doing is we're treating our sequence, right? Our sequence, we've got these integer values, these natural number values for our domain. So my sequence is really these points here that I'm plotting. Well, doesn't this show the definition is still true for convergence, that eventually, right, if I create a trap, an interval, eventually, I'm gonna switch to blue here. We'll do black. Eventually, looks like that's my n. For any natural numbers past that n, my sequence sits inside that band. Because after all, my function sits inside that band. And those sequence values are just individual values of the function that the function takes on for natural number values in the domain. Okay? All right, so let's try one. Let's find the limit of the sequence defined by this guy. So what I'm gonna do is I'm gonna take advantage of the fact that the limit as, well, actually I should say this. Sorry guys. I should start by saying let f of x equal 2x squared minus 1, all over x squared. And now I'm going to take advantage of the fact that the limit as n goes to infinity of an is equal to the limit as x goes to infinity of f of x. Right? That's that previous theorem. So the limit as n goes to infinity of 2n squared minus 1 all over n squared is equal to the limit as x goes to infinity of 2x squared minus 1 all over x squared. And now using dominant term analysis, essentially saying that the minus 1 is not going to have any discernible effect on the value of 2x squared when x's are ridiculously large, this thing starts to look like 2x squared over x squared, which is just 2. Okay? So there we have it. Okay. Now, we also might be concerned with sequences that maybe they don't converge, but maybe they grow without bound. So maybe their limits are infinite. So what does that mean? Well, that means that for every positive number m, I can find an integer such that, and remember this integer, think of this as an integer from the domain of my sequence, such that all my sequence values are greater for anything past that large n, a capital N. In other words, let's say we've got this sequence, it's doing its thing, and then all of a sudden it starts to blow up. So this says that I can find an m, any m. So again, if I'm on the y-axis and I'm moving up and down and someone says, stop, and I stop, then the definition says, okay, well, eventually, all the sequence values will be greater than that m. And so look, I found that capital N. Notice it's right here. For all the sequence terms past, right, all these guys, the values are above m, okay? And this is true for any positive number m, so I could choose another one. I could call this one m1, call this one m2, move it up. And when I do that, notice, oh, I get a new n value. Everything past that is larger than m2, and so on. Okay? And so you get this idea that you can just keep pushing, you keep finding a floor for those sequence values. They have to blow up to infinity. Similarly for the case of the sequence tending to negative infinity. Okay, we also have some limit laws. I'm not going to go through all these. You've seen them in the context of real valued functions and continuous functions. Here we're just taking snapshots at really the natural number domain elements for these sequences, but there they are. Very intuitive, very familiar. We're just saying they also work with sequences. All right, so let's say we want to determine if that sequence converges. 5 to the n over n factorial. Huh, what do you think? Well, before we get to it, I'm going to prove a couple theorems. The first is the squeeze theorem. And so we can have 3 sequences, AN, BN, and CN. And notice that AN lives between BN and CN, at least eventually. If BN and CN have the same limit, then AN needs to have that limit as well. In fact, it must, because here's the situation. Let's say that here is I'll call this my L. Blue will be my CN. And I don't know, let's make black my BN. And then AN, if AN is trapped inside, then because it can't go past above CN and it can't go below BN, if BN and CN are coming together, then it's trapping the value of AN. They have to have the same limit, okay? That's the squeeze theorem. Very useful theorem. Okay. We also have this important result, which actually takes advantage of the squeeze theorem. So if the absolute value, if I get a new sequence of the absolute value, if that is equal to 0, then the sequence itself converges to 0. And so here's the proof. Well, here I've trapped AN between the negative absolute value and the positive absolute value. And so then what this tells me is, assuming these limits exist, which I know they do, let's see what happens. Well, absolute value of AN, that's going to 0. So if I take the negative absolute value, that's also going to 0. And so what do you know? The only way for that to be true, right? We use the squeeze theorem. That limit must be 0, okay? All right. So let's take a look at this. Now, you look at this and you may wonder what, and you know, if you don't have an idea of what the sequence looks like, you might write out some terms. So watch what we got here. I'm going to write out a few. I'm going to say, just going to write out some. So we've got 5 over 1. We've got A2, right? Actually, I'm going to do this. I'm going to say AN equals, let's just get an arbitrary AN. So 5 over 1 times 5 over 2 times 5 over 3 times 5 over 4 times 5 over 5 times 5 over 6 times all the way up to 5 over n minus 1 times 5 over n. Now, you may be thinking, so what? Well, I'll tell you what. These terms here, that's just a constant, right? That's a constant. I'll call it C. You're welcome to figure it out if you want. You can figure out what that constant is. 5 to the 5th over 5 factorial. But all I care about is that it's a constant. And these terms are all less than 1. which means as a product, those terms are decreasing in value, right? And so what I can say is that these are all less than or equal to C times whatever that last term is, 5 over n. Okay. Now, look what we have. Well, 5 over n, that goes to 0. And so by the squeeze theorem, the limit as n goes to infinity of 5 to the n over n factorial equals 0. Okay. That squeeze theorem is very, very convenient, very useful. All right, let's look at the geometric sequence. That's a sequence you probably recognize. But I want to look at some cases. So for case 1, let's let R be greater than or equal to 0, and let's make our C positive. Okay. I'm going to let f of x equal C r to the x. And so case 1a, if you will, zero is less than or equal to r, which is less than 1. Well, we want to talk about convergence, right? So using that theorem we talked about earlier, a few slides back, and this. And what do we know about R? Well, R is what? Well, R is less than 1, right? That was our assumption here. And so if I have something less than 1, well, and positive, right, being raised to an arbitrarily large value, we just get 0, okay? Well, how about case 1b? What's another possibility for values of R? Well, R could be equal to 1. Well, this doesn't seem too terribly interesting. That's C times 1 to the n. That's just C, right? And then the last case would be if R is greater than 1. Well, if R is greater than 1, then notice that R to the n is growing without bound. So we get infinity, okay? So this is our case 1. Well, what about if R is less than 0? And of course, C wouldn't be 0, otherwise that wouldn't be very interesting. Well, let's play kind of a similar game. So case 2a, we might say that R is between -1 and 0. Well, watch this. I'm going to turn this around. Let you convince yourselves of that. And then the limit as n goes to infinity of C r to the n will be 0, right? We showed that last time because the absolute value of R is between 0 and 1. And you know what, maybe I'll do this just to kind of bring things home for you. Right, so we get 0. All right, well, if the absolute value is 0, then we know by theorem, I forgot the number, but the sequence itself converges to 0. And then 2b, well, if r is negative 1, then this series alternates indefinitely. Between negative c and c. So it diverges. Okay. And then my last case here, we'll say r is less than negative 1. Well, if that's the case, the series alternates sign and in absolute value, right, that thing goes to infinity. So it diverges. Okay. All right. So here's an example. Look at this one. Limit as n goes to infinity, negative 1 to the n over n. Well, let's think about this for a second. What happens to this sequence? Sorry, right like that. Isn't this just 1 over n? And that converges to 0? And so since the thing converges to 0, right, since the absolute value of the sequence converges to 0, then we know that the whole thing converges to 0. Okay? Now, I want you to be careful. Just because the absolute value of an converges doesn't mean the sequence itself converges. We've seen that it converges when the absolute value is 0, and the absolute value converges to 0, but what about more generally? Well, let's consider this sequence, negative 1 to the n power. Think about negative 1 to the n. Negative 1 to the n, there's 1. There's negative 1. 1, 2, 3, 4. This thing lives between. And when I say between, I really mean or, either or, right? It's either at, it's either at negative 1 or 1. Okay? This thing diverges horribly. But the absolute value of an, that's just 1. Well, that's pretty darn good convergence there. So here we have the absolute value converging, but the sequence itself diverging. So be careful that you don't extend that theorem that says if the absolute value an converges to 0, then the sequence itself converges to 0. It's that special case of converging to 0 that makes it true. If it doesn't converge to 0, you know, we have this other situation. Okay. All right. This is a nice theorem. Again, the proof is a little bit beyond the course, but essentially the limit of a function is the function, the limit of f of an is f, the limit of an. And so that's kind of a nice result. Let's apply this theorem. So in other words, the limit as n approaches infinity of cosine 2n minus 1 over n plus 5. Okay. And so, oh, you know what? I'm gonna make a little real-time edit here. I don't like the way this. I want this actually to work out a little nicer. Let's call this. Oh, let's call this just n up here, n minus 1. And let's call this n squared. Okay. And so we can call this cosine of the limit as n approaches infinity of n minus 1 over n squared plus 5. Now, from dominant term analysis, we know that that limit is 0. What's cosine of 0? Oh, well, 1. Right? So there we go. All right. The last thing we're going to turn to here is some special conditions that guarantee convergence. Okay, namely bounded and monotonic. And I'll explain what that means. Monotonic means decreasing or increasing, or as I've written here, increasing or decreasing, meaning the function or the sequence is going up or going down. Bounded above means that the sequence values are all below some value, and bounded below means they're all above some value. Okay? Now, is being bounded enough to ensure convergence? Let's think about that. So let's say that I had a sequence that's bounded above and below. I'm going to call this M1 and M2. So all the terms of the sequence live in here. Well, does that mean that the thing has to converge? No. But what if instead, right, if we could add a condition notice that this one converges. It's increasing, bounded above. We could go the other way too. We could come down this way. We could say, all right, well, what if we've got oops, this one. This is decreasing, bounded below. So if you can add monotonicity, meaning it's only increasing, only decreasing, with the appropriate bound above or below, then we can ensure that we have convergence. Again, that's very intuitive, right? You know, and again, this is one we're not going to prove, but increasing and bounded above gives me convergence. Or decreasing and bounded below. Notice also that we're not actually asking what it converges to, right? A lot of times that's not the issue. We don't really care what the sequence necessarily converges to. And I want to be careful. That's not true always. I mean, sometimes there's plenty of times when we care, but it's a little more, it's a more specific question than simply of convergence. In fact, before we try to go even look for what it might converge to, it would be worth deciding if it converges at all. Otherwise, it's like going on a hunt for something that doesn't exist, right? I could grab my gun and my pack and my beef jerky and head out to look for Bigfoot. That doesn't mean he's out there just because I'm equipped to look for him, okay? Are some of you wondering, oh, he's out there. I've seen him. Well, that was a cooler that happened to be called a Yeti. Don't get crazy here. Okay, so convergence. So let's see how this works. Prove that an equals the square root of n plus 1 minus square root of n is a convergent sequence. Well, let's start by saying or proving that an is bounded. Okay. And so what I'm going to do is I'm going to take, and this might not be so obvious right now, its boundedness, but watch what happens if I use the conjugate. When I do this, my numerator becomes n plus 1 minus n, just 1. My denominator becomes n plus 1 plus the square root of n. Well, this is greater than 0. It's greater than 0. I mean, I could even do better than 0, right? It's greater than 1 plus the square root of 2. 1 over 1 plus the square root of 2. I don't know, but I don't want to think too hard. My numerator is positive. My denominator is increasing. This thing's greater than 0, right? Positive over positive. Now, an monotonic. Well, how do you decide if something is increasing or decreasing? Oh, well, we have something we can use for that. How about we take the derivative? Let's let f of x equal the square root of x plus 1 minus the square root of x. Then f prime of x is going to be equal to 1 over 2 square root x plus 1 minus 1 over 2 square root of x. Well, let's think about this, right? For x greater than 0, because, well, I'll even say, let's say for x greater than or equal to 1, right? Because we're talking about the sequence values. Think about these denominators. This is a smaller denominator. That one is a larger denominator, which means this first quotient is positive but smaller than the positive second quotient. Oh, that tells me this is negative. All right, so an is decreasing. So decreasing and bounded below tells me that an, the sequence an, converges, okay? So that's a good review and extension. Like I said, we're going a little bit deeper into what sequences are and how they behave. Again, the big ideas, convergence or divergence. How do we know? Well, we ended with this wonderful result, bounded monotonic, right? This thing is, if a sequence is increasing and bounded above or decreasing and bounded below, then we have convergence. We had the squeeze theorem and some other tools that we looked at. Where we go next is series. So we're essentially going to take the terms of a sequence and add them. And then once we do that, we're going to build a new sequence of partial sums and ask the same questions. Do the series, or does a given series converge or diverge? Because again, keeping our eye on the big picture. Can we write certain functions that are not polynomials as some sum of terms, polynomial, on an interval? And to do that, we have to talk about convergence of series. So that's where we head next. Get your hands dirty with these, work some problems, and I will see you soon. As always, happiest of studies.